Welcome to my video walkthrough of functional programming. I'll be using examples and quoting this book, Mostly Adequate Guide to Functional Programming, but also putting my own spin on things. So to start out, we have an example of a class called flock. We're just going to console log out what this code does. So we're doing some conjoining where we add seagulls and breeding where we multiply. So this gives 32. But it looks like it should give 16. So we start with flock A, 4, we conjoin flock C, which is 0, we breed flock B, that doubles it, 8, and then we conjoin to A times B. What we don't realize is flock A got mutated in the process, so we got 32 instead of 16. So down here on line 23, flock A is no longer 4. It was modified in the previous steps. And so that's mutability, and that's the argument for immutability, which means variables do not change over time, which makes your code easier to reason about. So let's go ahead and rewrite this in a functional programming paradigm. So I'll create a new file over here, yfp.js, and I'll paste in the functional programming example. And so this example is immutable. No state is changing anywhere. These functions here on line 1 and 2, conjoin and breed, they just return new values. They don't hold any state internally, so they're pure. And we'll get more into that later. So then when we run this, yfp, instead of getting 32, we get 16, which is what we expected to get. So the code is easier to reason about when it's written in an immutable manner. There's no longer state being mutated that's hard to reason about. So I know it's a mathematical example. It's kind of like an easy example, but we'll get into some real examples later. So I'm going to go ahead and rename conjoin to multiply, and conjoin should actually be add, and breed could be called multiply. So that's another concept in functional programming, is try to get to the bottom of the concept. Really, these things are just add and multiply and should be named as such. So once this refactoring is done, this code's a little bit easier to follow, but there's still some problems here. And to demonstrate this, let's create a new file, and we're going to touch upon some mathematic concepts here. So I'll just paste in this example code here. So this is the functional example that we just created, and we can say that add of x, y added to z is equal to add x to add y, z. So x plus y gives you a sum, and then adding that sum to z is the same as adding y to z and then taking that sum and adding to x. So we can group that either way we want, and we get the same result. So let's go ahead and fill in these values here so we can actually run this code and test it. And if we run that here, we get true. So adding x to y and then adding that to z was the same as adding y to z and then adding x. So that's the associative property in mathematics. So we can group it. Next is the commutative property. And so this one is going to say that we can add x and y, and that's equal to adding y and x. So we can change their order. It doesn't matter what order. That would not be true if we were dividing numbers, because 4 divided by 2 is 2, and 2 divided by 4 is 0.5. So division is not commutative, but addition and multiplication both are. Identity is pretty simple. Basically, adding x and 0 is equal to x. So the identity is preserved. And if we run that, we get true, of course. So adding 0 to something has no effect. And then the last one is distributive property. And so for this one, we'll start out with multiply. And we will multiply x and the sum of y and z. So y plus z gives us a sum, and then we multiply that to x, or by x. And that's going to be equal to first multiplying x and y, and then multiplying x and z, and then adding those together. And if we run that, true. So it doesn't, don't worry if you don't know all these mathematical principles. The idea here is that there is objective ways your code can be simplified. So let's go ahead and do that now. And imagine that like the compiler could do this for you one day. Like if you wrote this code, the compiler could do this. So it could go through and apply the associative, distributive, identity, and commutative properties to your code and simplify it just like we're doing here by hand. And in fact, there are tools out there that let you do these types of things. So think of type checking, like TypeScript or Flow, where it goes through and sees your function expected a number, but it was actually passed a string, and it does like some extra analysis and catches bugs. In the same vein, a functional paradigm would allow the compiler to go through and make performance optimizations or flag code that's overly complicated and suggest a simpler alternative. So this is like a simple recipe we're following here to simplify it that has mathematical proofs. And we end up with much simpler code that does the same thing. So these are just some of the benefits of functional programming, and we'll get more into the other benefits later. I just wanted to start out with this example. And if you like this video, make sure to thumbs up, comment, and share, and stay tuned for the next video.